Well, this leads me, I mean, I'd like to ask the question of the community about, again, I raised the question of disks. Like we've got all these possible disks. We've seen a number of different disks show up in the talks. And, how, on a, how do we know which disks we're supposed to be focusing on? Since we often can't resolve the central engine, it seems like we have a bit of degeneracy in our models with, disks around from the primary disk or disks, a secondary that was torn up, a secondary that's still there, but it's a secondary disk, circumbinary disks. And it's a little bit worrisome in a way because it gives us a lot of freedom in our models, maybe more freedom than we want.
The jet velocity is about the escape velocity. So if you form around a companion, say main sequence, it would be 300 kilometers per second, multiplied by 3, divided by 3. But if it's around the whatever core left over of the AGB, it might be faster. Also, it has lots of radiation. So, and I don't know how you form a disk there. It's not easy because you need it will not be long-lived. Because of the high radiation and high temperature and everything. So I think we are mainly looking for disks around the companion. This is my feeling in planetary nebula.
But what about in common envelope, like, post-common envelope? Because as we've shown here, you may shred.
Yes, circumbinary. You can have a circumbinary disk, yes. I don't know if it launches jets, but definitely you have a accretion disk. Then maybe also you can, I don't know around the central stars, but the luminosity is so large of the central star for these kind of systems, so I'm not sure the accretion disk will survive close to the center. I prefer an accretion disk around the companion, but I don't have a proof of that. I bet all your money on that. So
can I say something?
Yes.
Yeah, so we have a very well-known example, one example in our galaxy, which is the Boomerang Nebula, where we know that it went through common envelope evolution. We know that the two stars merged, and we know that it has to have a disk because it's producing these beautiful collimated structures emerging from it. So here's a case where we know all these things happen. The question is, how do you make it?
What is the velocity of the jets?
Hundreds of kilometers a second.
So it's not, okay, it's not the core. It might be a merger product. Then the question is, what is a merger product? How do you know it's merged? How do you know you don't have a binary still there?
Well, because when we do so we know how much mass is being ejected. And so we know the amount of energy which was needed. And so in order to release that amount of potential energy, the separation of whatever started has to be smaller than the current size of, what is at the center. So, I mean, we know the spectral type of the star at the center. So we know what is, and its temperature, so we know what its size is. And so in order for us to for it to have given the potential energy converted into kinetic energy to produce the wind which is coming out from it, we know that the separation now has to be smaller than the size of the current star.
Can you show us because we are doing with morphology, can you show it's a discussion? We have time. Like, Vendra, can you upload and share the picture of the Boomerang nebula?
Not immediately, sorry.
No, just that we show if we are convinced about what you say. So I don't know if I put just in Google Boomerang, I get different picture. I don't know which you prefer.
Well, you should look at our ALMA paper and which shows both the Hubble. So it shows the central part where you see the very collimated lobes coming out of it, both in scattered light in the Hubble images and in our ALMA molecular gas images, molecular line images. But I don't have that in front of me. So, I mean, I can try to get the paper and then, we can look at the paper together. So.
Do you see my screen?
Yes, there you
Which image should I look at?
The red one. Yeah, this one.
Okay, this one.
Yeah.
Okay. So if you ask me and you asked me, I will tell you it might be a triple star system. Look how non-unspherical it is. There is no real axis symmetry. One lobe is not like the other. So we might have gotten the energy by merger of two other stars, for example, two main sequence stars or something. So I would say it's very complicated. And we should be open-minded. If the velocity is few hundred kilometers per second, I would say it's a main sequence star. It can be a merger of two low mass main sequence stars in the envelope or something.
I'd like
it's not any more complicated than what you see in multipolar planetary nebulae. So
right.
Yeah, it's more asymmetrical, but we should discuss it.
Yeah. Can I also, because there's some comments in the chat that I wanted to bring up. So there was some discussion about the rings. So Joel brought up the point that the intruding jets are 100 years old relative to the ring. So I just thought there was a discussion here. And then Alberto has brought up a point, and Guillermo has brought up a point. So does anybody within that discussion about the rings want to chime in? There was a question about the interaction between the jets and the rings.
No, I'd love to, Adam, just for a second.
Go ahead, go.
I'd really like that, like you said, the young people to start taking over the conversation. But the simulations that Vero showed were just so beautiful in that, to my knowledge, that's the first example I've seen of this binary-induced spiral pattern that happens during the AGB mass loss phase. I think we can all say that with some certainty now. And then that's being badly disrupted by this new flow, this new collimated set of flows, complex flows from the central object. And that's when the planetary nebula, it seems like, is turning on. Mm-hmm. And so, it's a very interesting, I think, kind of provocative model. We tend to think of planetary nebulae as like 10,000 years old. But I think this may be showing that some planetary nebulae, at least, have emerged from the AGB just, literally like 200 years ago or something like that, 300 years ago. And we're seeing that happen. So, I think for me, that's like a bit of a game changer. And I don't know about how other people feel, but, maybe we kind of knew this already, but I think the simulations are now showing that that's a really viable model.
Yeah, I agree. I think those were really beautiful simulations in that way.
What is a game changer, Joe? I didn't understand.
Oh, well, just that I think, for a long, long time, people have been imaging these large structures, spherical structures around planetary nebulae. And because they're ionized, we think of them as tracing the history of the planetary nebula as being, 10,000 years old or more, because that's the dynamical age of these spherical ring-type structures. But in reality, it's probably the ionization that's turned on that much more recently, and the rings, ring-shaped structures way predate the onset of the quote-unquote planetary nebula. Yeah. Vero, please tell us.
I'm gonna go. I'm gonna crash it.
Go for it. Dude, go.
So yes, I think that is like quite. At least for us, it was like a highlight in the simulations. And also, as you were saying, the spiral structure that is before, that is older, then you have the planetary nebula. And in the cases that we were adding the jet, also, because I misunderstood Denise, I think, I don't know if I apologize for that. So also when the post-AGB phase starts, so it's a game in between times of the spiral, the jet, and then the AGB, which was giving us like really different morphologies. And it was this period of the binary. So the material is just expanding, and then one can see there that all these structures also, they have to expand in between the rings. So it's low density and higher density. And that was a huge, how you say, a huge morphology changer in our simulations. so, and we didn't intend to have a certain morphology. So it depends. The jet, in our cases, it was precessing. So it will let the jet, and with a fixed angle. So we did not have like a parameter study. It was just one and to see what happens. So when it was precessing, of course, it depends where it's going, and you're seeing the jet, and then you start the post-AGB phase, that you have this like a double, so like two fingers, let's say, because of the variability of this specific jet or not. So, or is still confined, even if it's you let the jet evolve the same amount of years, the difference in the binary period changes a lot, that part.
Thank you. That's interesting.
Romano, I'm gonna have to step away after this, but Romano, if you have, hello, Romano, good to see you.
Yeah, hello, everybody. Just to complete a bit the information about the rings, we made a study, it was in 2004, about the time scale of rings. And indeed, I mean, the rings are in the halo. The halo is the HB envelope, and then it's photoionized during the planetary nebula phase. But we estimated that the mass loss modulation, regardless from what is produced, takes place during the last something between 10,000 and 20,000 years of IGB evolution. So it's not a matter of a few hundred years. It's something that lasts for 10 or 20,000 years at the very end of the IGB evolution. And also we saw that the spacing between rings increases with time. So in protoplanetary nebula, rings are more close to each other, and then they become more spaced because, of course, as Albert was mentioning, there will be some photoionization go through and some dynamical evolution of the density structure around the planetary nebula.
Yes, also Isaac Gonzalez Carvajal is the one that is studying how the rings change, let's say, because of the AGP, post-AGP phase also. Yes.
Let me add to what Romano just said. About, what was it, 7 or 8 years ago, 2 papers on the myriad rings, the many rings around CRL 2688 appeared in the literature, and they included proper motion studies. And those rings appear to have been, each ring is ejected at a different time. And the length of time over which the rings were ejected was many thousands of years. Now, inside all those rings are globes, but they're velocities. I wrote a paper on this, and I can't remember what we found for the kinematic age of the lobes. I think about the same as the rings. Or about the same as the last ring, let me put it that way.
The kinematic age of the rings, Bruce, is, sorry, not of the rings, but of the bipolar, well, multipolar structure is on the order of 50 to 100 years, based on the CO mapping done of that object with the RAM interferometer.
So something goes on over and over and over again, produces the rings, and then presumably an event like a merger takes place, and out pops the planetary nebula that we love so much. Now, NGC 7027 has several different dynamical time scales. Its ring, its bright ring, which is seen well in the radio and the optical, has a dynamical time scale, if I remember it right, of 1,000 years. But these little arms and legs that protrude from there have a much younger time scale. So 7027 just is a renegade. It's very difficult to take a look at it and make sweeping generalizations.
Wait a moment. I'm a little confused by what you just said, Bruce. When you said the ring in 7027, you're not talking about equatorial?
I mean the bright elliptical ring that I would call the actual, the one that hasn't.
Are you talking about the things which are seen scattered light in Hubble, for example? There are 3 or 4 in NGC 7027.
I guess I should talk so you can see NGC 7027. Blah, 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 blah. Did that work?
So yeah, the rings which are seen, the bluish things which are seen in, I think, in scattered light, those
Yes.
are, from the AGB phase, I would imagine. So I don't see
Yes, right.
why do you call this a renegade in any way?
No, it's the arms and legs. You see a clover pattern.
Yeah, and those are of course happening during the, the same kind of phenomena I would imagine, which is happening in all preplanetary nebulae. That is, you have something which produces jets, and those jets can be multiple jets or jets which are moving their axis or wobbling or whatever, and producing these.
They have numerical timescales that are much shorter to measure their proper motions.
Yes,
The inner stuff that's inside that very bright ellipse, it's expanding at about 20 kilometers a second if you believe the Doppler shift measurements. It's very, very complicated. The proper motion studies, however, of that ring give a much shorter dynamical age, more like I'd have to go back and look at the paper. Sorry, my memory.
Yeah, I could say, Bruce, that the expansion of the rings, when you look at the proper motion, they point at some time of about 1,000 years. But this is, of course, difficult to assess because those are the innermost rings, and they may be affected by dynamical effects or photoionization and so on that are going to destroy the rings at the very end. So we are looking.
Martin, I think the point is each ring is moving outward at the same speed. So the larger rings are much older than the smaller ones. So there's a spread in ages there. The dynamical age we measure is for the bright inner rings, not for the ensemble.
Yeah, definitely.
And just to, I don't know if it was clear, the time scales that Vero was showing, it was just the post-AGB evolution of the simulation. It was not about the time that it took the whole spiral in order to fill the whole computational domain. So these are young post-AGB objects we are simulating. That's why the ages are so, like the order of 100 years.
Yes, I thank you. Yes, I forgot to say that. So the spiral is much, much older.
A wonderful student of Joel's has done a star and its SED. She finds that star in the center is, as I think we all would have guessed, a really massive central star among PN nuclei. So the particles evolve very quickly, and yeah, that makes this nebula a monster, right?
Vera, could you remind us what the orbital periods were of the objects that were producing the binaries at the time they're producing the spirals?
Yes, let me just open the presentation because I closed it.
Remember numbers like a few years or something like that, but
if you allow me, I can share the screen just for you to see the parameters that we have. Okay, so a main of 0.7 solar masses and 2.5.
So as we all know, merging black holes produce bursts of stuff which whose frequency goes way up during the merger. And from what I can tell just by looking at your figure, this binary system doesn't merge or isn't allowed to merge. Could you clarify that?
You are saying that because we do not resolve both stars?
Well, I'm saying the separation between the rings is the same throughout, and that wouldn't be the case if the stars are getting closer to one another, right?
Oh, yes, yes. I mean, this one is in a circular orbit. They're not getting closer in this case. They're just in the circular orbit, and that's it. There is no like, dynamics between stars. I mean,
Yeah,
evolving.
thanks.
Yes, no. Mm-hmm.
Yeah.
And then also, I am sorry because I made a mistake in this graph, because it was in the conversation, they were asking about this elliptical features, and it's my mistake in this figure. It doesn't have the same region, the image. Sorry for that. That's why it appears really elliptical, because it was mentioned that why we did not see that if it was a projection effect. And of course, as Jesus was mentioned, there's some of the projection effect, but it's not like that. It's my mistake, it's not the same region.
So Vera, it's really interesting though, again, you know, it's worth stressing that the orbital radius of the pre-existing binary, you know, perhaps it's changing, it's probably spiraling in, but still it's about 120 AU and your AGB star swells up to 150 AU. So the event, presumably that is causing the jets is common envelope.
Wait, AGB starts swelling up to 150 AU? No.
Yeah.
Yeah, that just seems.
No, that's impossible. AGB stars are like a few AU maximum, right?
Right. Joel, maybe just.
That's like a supergiant radius. Sorry, yeah.
So maybe there's a stable accretion disk with a jet, which is in orbit around somebody, which produces a spiral. Who knows?
So there is no chair to this session.
No, I'm actually acting as a chair because
okay.
Alan has to leave. So, Noah, could you comment a bit more on Priscilla's question?
Yes, we have what we call a class of messy planetary nebulae, which are planetary nebulae that lack any symmetry. Actually, maybe a symmetry, mirror symmetry, but usually they have no symmetry. And these planetary nebulae with these deep, crazy shapes, maybe I can show if
sorry for advising.
Yeah.
Sorry.
If you release a share screen. So there are different planetary nebulae, and I think the only explanation triple, but we as well expect a planetary nebulae to be shaped by some. Here we have these planetary nebulae. You can recognize give credit to people here if you like. So we expect that some binary will actually be triple. This is everybody expected. And yes, so I think in many cases we have triple evolution, but I don't know how to connect it. It's very complicated. For example, we have one star that swallow a binary system. So now we have common envelope is a binary inside the envelope. This is one. Then we can have closed binaries, and the tertiary star is far away, but still has its influence. And the two, if you have compact binary entering the envelope, the two compact binary might merge in the envelope, or one of them can ejected and set the remaining two stars in the common envelope with velocity to the side. There are many, many processes. They're not talking about two stars accreting mass and launching two pairs of jets. And when you look on these planetary nebulae, we call them messy planetary nebulae because we think this is the best description.
I see. I have a question for Alejandro Raga. It's very interesting the way that you can produce flows with the Hubble law or homologous expansion, but we sometimes see very elongated jets with this kind of expansion velocity, can you produce this kind of very elongated jets? Maybe if you fine tune the densities of the two media?
It could be, or if not, it could be a jet, no, with continuous ejection from the source. And if you want an ejection velocity that decreases with time, then you could have also a ramp. No, you could have a jet ejection and an outflow velocity that decreases as a function of time. You would have like a ramp of lower velocities towards the source also.
Actually,
there
when
are
you have
many ways to do this.
yeah, actually, another way is when you have an explosive event. Actually, the things that they are moving faster, they get farther away, and this is a way to have a velocity increasing with distance to the center.
Well, and this is what happens in this clump model, if you want. The bow shock produced in the high density region. When it gets liberated, when it goes into the low density region, there's this velocity sorting mechanism that you say, no? This is what is happening in this flow too. No?
Yeah, it's a kind of explosion at that point.
You suddenly release material with different velocities, and then it, no, it's the faster material goes ahead compared to the slower material.
Okay.
What do you say? We agree completely.
Okay. Is there any other question or comment?
They say young people, so I have a comment, but I prefer really if anybody young, but then we have the Slack. So I have a short comment if I may.
Go ahead. Go ahead. No, I'm checking the Slack channel.
Okay, so my comment is this simulation that people mentioned, Bruce, I don't know if Bruce is still here, but this nice simulation of two winds colliding, this is a very nice simulation with instabilities and so on that we see here, but I don't think the red rectangle is the best object to explain with this simulation. I look carefully in the break on the red rectangle, and you see these shapes that you see that I marked with a yellow curved line. You see kind of it's turning around, and you have very bright kind of structure that I prefer jet. Also these post-AGB stars, now the group of Hans van Winkel discovered more and more jets. So I think jets playing here the major role. Can be also spiral structure or something, but I'm not sure this is the case. But
I'm so sorry to interrupt you. I'm
yes.
so sorry. I'm sorry. But I think there's been some simulations with jets to reproduce the rectangular nebula by Wolfgang Steffen, I guess, and Alejandro Esquivel, that I don't know. I know they're in the conference, but I don't know if they're still there, because I know there's been some simulations, as you were saying.
Yeah, there are different papers on shaping the red rectangles, yes. But this say nothing about the simulation. The simulation is great, and we should explore them. But just, I think the red rectangle is more complicated. The companion is outside. The orbital period is only 1 year, and it's complicated. But we might, maybe using jets and this spiral structure to explain the red rectangle. This is my comment.
No, and this is Bruce. The last slide that you showed, I think for any reasonable observer,
I lost
the model.
Bruce, we are losing contact with you. Don't speak while you're on the other side of the moon.
My internet has been a little. Can you hear me okay now?
Yes.
Kind of.
So what I said is, in that image that you showed just now, with the model and the real image, I think any observer except the most cantankerous one would say perfect fit. I mean, it just doesn't get much better than that.
Bruce, but you are not an observer anymore. You are a theoretician now.
Well, that takes me. So I
Still.
lost my mic.
I'm sorry to interrupt, but Bruce, you said it correctly. Other than the most cantankerous, looker,
Yes.
and of course we have no soaker here, our friend.
Okay, guys, I think we have reached the limit for today. It's been a pleasure. And I would ask you to unmute and clap to all the speakers today in both sessions. Okay, so we'll meet again tomorrow. It's going to be again 13 o'clock GMT. Remember GMT, and then we have the next session is going to be on White Dwarf, and the chair is going to be Howard Bond. Okay, so take a rest, whatever the time is at where you live now. We'll see each other tomorrow. Bye-bye, guys.
Good night.
Mhm.